Now this is recorded and how to jump out of this. Okay. I hope this is more or less.
Yeah.
Okay. So we're completely done with the preparation. Hello, everybody. This is the next part of our seminar for mathematical physics. Today, we are happy that our invitation has been accepted by Mauro Mantegazza, who is a postdoc researcher in the Mathematical Institute of Charles University. And as we announced, he's bringing for us a very catchy topic, jet functors in non-commutative geometry. It actually combines two interesting topics themselves, but Mauro decided to combine it to something even more fantastic. So we can, I think, can look forward to your performance. Thanks for coming very much, and thank you for the invitation.
So how do I move the slides here with arrows?
Yeah.
Spoilers.
Okay. Okay. So, not very good.
No, that's okay. Okay, so what I'll be talking about today is a project with my two collaborators, Keegan Flood and Eric Winter. And more specifically, I will talk about the contents of a paper which you can find on the archive with the same title as this presentation. So what I'll be talking about today is a generalization of jet functors to the generic setting of non-commutative differential geometry. So let's start with what we mean by non-commutative geometry. So in geometry, what usually happens is that we have a geometric object and we want to study it through algebraic means. So what we do is we take an algebra of regular functions over this geometric object, and we proceed to study the algebra. Now, what does regular mean? The meaning of regular depends on what we want to study. So we want to study smooth geometry, so differential manifolds. We might take the algebra of smooth functions. We want to study complex geometry. We might take holomorphic functions or complex value smooth functions. If we want to study algebraic variety, we can take rings or polynomial rings. So what happens is that if the correspondence is good enough, then we obtain an equivalence of categories between our duality, between the geometric category and the algebraic category. And furthermore, once we have this equivalence, we can proceed to forget about the geometric object and study directly the algebraic one. Then once we have an algebraic object which represents the geometric objects well enough, we can proceed to generalize this object. And that's what we do. So we start from, we want to generalize the notion of smooth manifold. And what we forget about our algebra of smooth function is the commutativity. So instead of taking as algebra of regular functions, we take a generic unitary associative algebra of a ring. So let's see a table of translation between the various topics. So we start from the geometric complex. We can have real or complex manifolds, and this will be translated in algebra by the field we use, which is R or C. Non-commutative different in our setting. This field will be substituted by a generic commutative unitary ring. Now, as I said before, the manifold M is encoded algebraically as the function of the algebra of smooth functions over it with real values. And for us, this will just be a unitary associative K algebra. Now, a vector bundle, which algebraically corresponds to the infinity n module of global sections, will correspond in our setting to a left A module, a generic left A module. But even more, we know by the Serson theorem, as we saw a few weeks ago, that there is an equivalent, the global section functor is an equivalence of categories between vector bundles and finitely generated projectile-less modules. So for us, a good generalization of bundle is a finitely generated projectile-less module. And of course, a map of bundle, which classically corresponds to a C-infinity and linear map, will correspond to just the left linear map between the modules. Okay. Now, a few definitions, a few properties that might be useful for us that modules can have are flatness and projectivity, and of course, finitely generated projective. This will be the notation that we use. So left modules will have the A on the left, and the right modules will have the A on the right. And then these are the categories of the properties I mentioned before. What I want to stress in particular is the notion of flatness. Flatness, which means that the functor, the tensor functor of that module is exact. Now, this functor is usually just right exact, but we ask also that it's left exact. The reason why I want to highlight this point is that this doesn't correspond to the geometric notion of flatness, which is instead a very rigid condition. So asking that there is a connection which has vanishing curvature. This is not what we are asking. This algebraic property corresponds geometrically more or less to the local triviality, which is a property that makes sense to assume for vector bundles. And in fact, as I said before, vector bundles correspond to finally generated projective modules. And as you can see there, finally generated projective modules are in particularly flat. So any object which is reasonable to assume it will be a bundle, it's also reasonable to assume that it will be flat. So it's not a strong condition. And then, of course, we have projectivity, which is also the algebraic notion, which means that it's an object B such that for every map from B to the codomain can be lifted compactably to the domain. Okay, so far I've only described the algebra of function, but this mostly includes the topological properties of the space. We haven't, in fact, talked about the differential properties of our generalized geometric object. And in order to encode that, the differential part, we define the so-called exterior algebras over A, which want to generalize the notion of the Dirac complex, essentially. So differential forms over this. Okay, so what is an exterior algebra over A? It's an associative graded algebra where the zero grade corresponds to A also as an algebra. And it's endowed with a k-linear map D, which increases the grade by one. It has these three properties, the usual complex property of complexes. So this square must be zero, must satisfy this graded Leibniz. And furthermore, we ask that A and the exact forms generate the whole algebra via the operation. Now, these are exactly the properties of classical exterior algebra. The only property that we're not asking is the graded commutativity. And that's because that would force in grade 0 the commutativity of A, which we want to avoid. So as I said, the Dirac complex is an example of this. And now we'll see a purely non-commutative example, which is the universal exterior algebra. How does it work? So the grade 0 is fixed, as we said. The grade 0 is just A. The grade 1 will be the kernel of the multiplication, the linearized multiplication from A tensor A to A. And the differential will be defined so that the differential of A will be 1 tensor A minus A tensor 1. And we can see that this clearly belongs to the kernel of the multiplication. For higher terms, we just complete it to the tensor algebra. So the operation just becomes the tensor. And the differential, thanks to the three properties I mentioned before, can be uniquely extended to the whole exterior algebra from the zero grade. Okay. Okay, perfect. So this is a very nice algebra, very algebraic, but the problem is that it's too nice. It's too regular. And in fact, we can see that it doesn't really encode much geometric information beyond the algebra A itself. In fact, we have this property, this universal property that says that whenever we have an exterior algebra over the same algebra A, there is a unique surjection from the universal to the to our algebra, which is compatible with the structure. So the grading is preserved, the differential commutes, and the wedge. So, this mapping explicitly maps an object AI tensor BI into AI multiplied by the differential of the second. And notice that this is actually a bilinear map, not only a linear.
Is this surject?
It's surject.
Somehow universal also?
It's universal, yeah. And like for every other algebra with the same grade 0, there is a unique projection such that I think it's, so this is a universal. Okay, so now let's move back to classical differential geometry and let's see the object that we want to generalize. So we start from a vector bundle, E over M. This can be done in much more general context, but we'll just deal with the vector bundle part. And let's take a point in the base manifold. Now, every bundle is such that it admits around each point a local trivialization, which tells us that the bundle can be seen as the trivial bundle over some open subset of a real vector space. Now, using this trivialization, we define an equivalence relation between sections of the bundle B. So first of all, we use the trivialization to transform the information given by sections in real valued real functions. So now it makes sense to compute the Taylor polynomial of these sections, and we say that these two sections are in relation with each other if their nth order Taylor polynomial at the point corresponding to B in R agree up to order n. So their nth Taylor polynomial must be the same essentially. So it turns out that this definition doesn't depend on the trivialization chosen, so it's intrinsic. And it's an equivalence relation. The equivalence classes of this equivalence relation will be the njet of the section at the point B. How do we interpret this exactly? We interpret it as the nth order approximation of our section at the point B. This because any higher order deformation of our section will belong to Taylor polynomials of higher order. So this information gets forgotten, and the only thing we care about is the nth or the information up to order n. Okay, so it turns out that if we take the set of all these njets, the object that we obtain is a smooth manifold, and not only that, but if we map the jet at every jet at P in the point P, this is actually a projection of vector bundles. So the space of jet is a vector bundle, which we call vector bundle. Okay. Why are they useful? Because as we saw, they provide an intrinsic notion of Taylor approximation. Furthermore, as we saw last week, weeks ago, that they are representing object for differential operators in the classical theory. Furthermore, they're used also because of this correspondence. They're used to give a more general notion of differential equation, more intrinsic and general notion of differential equation, I think. And not only that, but they provide us a tool to understand where some equations have or not solution, like the Spencer theory. Okay, now a few properties, as we saw. So last week, the zero jet coincides with the bundle itself. This because the zero information is just the value of the sections at a point. So values of the sections are in E. This is the only thing that's remaining. Furthermore, we can recover the classical notion of Taylor if we take a chart X in variables x1, xn. And turns out that through the Taylor polynomials, the fiber of the njet at P corresponds precisely to polynomials, nth order polynomials in the variables given by the chart with values in the fiber of E at P. So the Taylor polynomial is exactly what realizes this isomorphism of vector spaces. Okay, now whenever we have a jet bundle, we also have a notion of jet prolongation, which I can also point out that it's not infinity and linear because it's not a map of bundle, but it's just a map between sections. It goes from sections of E to sections of the jet, and it maps the section into its nth order approximation. This is what it is. Okay, not only that, but for every n greater than m, we have a projection which essentially forgets the higher order approximation and maps the nth order approximation into its nth order approximation. Two properties: the zero prolongation is the identity, and the projection from n to itself is also the identity.
I have a question. Is the composition of projection and prolongation again some kind of prolongation?
Yeah, next slide will be shown. Yeah, okay. Okay, so it turns out that the operation of taking the jet bundle is functorial. It's functorial in the natural way. And the two maps, the two families of maps I described, so prolongation and projection, turn out to be natural transformation material. Not only that, but and here's the answer to your question. These are the relations between them. What do they mean? The first one is that if we take any section and we consider its nth order approximation, and then we forget the higher orders up to m, this still corresponds to the mth order approximation section. The second one instead says that if whenever we forget information from a grade to another, we can do it in one step, we can do it in more steps, it's just the same. The result is the same. Okay, so these are the properties. Now, what's our aim? Well, as I said, our aim is to find a notion of jet functor that fits the context of noncommutative geometry. How do we do that? We use a property which I haven't discussed yet. So what happens if we take the prolongation from n to its degree immediately lower, n to n plus 1, happens that this map is surjective and its kernel is the bundle of symmetric tensors. Why does this make sense? Because if we think of it in fiber-wise, as I said before, Jn has as fiber polynomials of degree n. So forgetting the last information means that I'm going from n polynomials to n minus 1 polynomials. So what's in the kernel is precisely homogeneous polynomials of maximal degree n. And this is exactly the fiber of symmetric tensors. That's why it makes sense. So this is at the level of bundles, but we can now use Serre-Swank theorem and apply the global section master, which is an equivalence. So now we have this short exact sequence in the category of infinity n modules that are currently generated and projected. And now we're in a context that we can actually use for the generalization. So how does it work? What do we want? We need to find a couple of families of tensors, one that resembles the symmetric tensors and one that resembles the n-jet. We also need to find a way of including the symmetric tensor, of seeing the symmetric tensors as jets, and a way of forgetting the information. And this must be such that this is a short exact sequence, and furthermore, we ask that there is a k-linear, and this again, let me stress this out again, it's not a linear, k-linear natural transformation from the identity to Jn. So it means that evaluated at each bundle, so infinity and module, the module will be mapped into its jet module. And of course, we need this two relation to still hold. So these are the minimal requirements for our notion to make sense. So let's start from the generalization of Sn. Before that, so in differential geometry, whenever we have this infinity module of differential forms valued in a bundle, we can interpret these sections as this tensor product of real differential forms tensor over infinity n, the sections of the bundle. So it makes sense also in the non-commutative context to interpret the algebras of exterior form as the endofunctors of the category of left-A modules. So we map each bundle into the bundle of differential form. So it's a tensor functor. Okay, once we have that, we can define the quantum symmetric forms, the functor of quantum symmetric forms. So we start, as in the classical case, by putting the first two degrees, 0 and 1, and 1 equal to the exterior algebra grades. This because there is no, below level 2, there is no symmetry to take into account. So this is the correct generalization. And now we define Sn by induction, starting from information of Sn minus 1, and we see Sn inside of omega 1 Sn minus 1. So the way we need to interpret this, this inclusion map, first of all, is essentially we are forgetting the symmetry in the first position. So we're mapping a symmetric, classically we're mapping a symmetric tensor into a one force into Sn minus 1, into symmetric forms of degree n minus 1. So we're forgetting the first, the symmetry between the first two positions. Okay, so what does this map mean and why it makes sense? So how does it work? We start from Sn minus 1, we apply the inductive hypothesis, so we can forget the information about the symmetry in the first position, and we go in omega 1 Sn minus 2. Now we apply the functor of omega 1d to this equation. This is a map. And now we have omega 1, omega 1. So now we apply the wedge. We apply the wedge and we end up in omega 2. So what does it mean? It means that we're taking the force with where the last n minus 1 components are symmetric, and we are saying that the wedge vanishes on that. Why does it make sense? It makes sense because classically the wedge represents a sort of antisymmetrization. So asking that the antisymmetrization vanishes means that the symmetrization vanishes. Of course, we are not asking the greater commutativity in this case, but still we can interpret the wedge operation as an antisymmetrization, quantum antisymmetrization. So its vanishing implies, yes.
So just going into pop. So omega n seems to be a bimodule in this question.
Yeah.
A. So if A is non-commutative, what is the structure of the right module?
In general, it doesn't. So E is an A module and it goes into A module. Am I?
Yeah,
Or you mean just this or just
omega n?
just this object?
Yes.
So it's an A by module. It's an A by module
Yes,
because
but
it has.
okay, so according to your definition of non-commutative differential forms, so what is the right A module structure of it? The last one is okay, so you have these D's, you can multiply
Yeah.
them
So
with
you. Well, it's just the one induced by the wedge. The wedge that in degree 0 corresponds to the multiplication by A. So in degree 0, the algebra with the wedge coincides with the algebra the algebra structure of A. So if you have a form omega, which by the surjectivity hypothesis you can write as A, the A1, the AN, then you can do wedge A, and this just corresponds to the multiplication. Then of course you can rearrange this and push the A here, changing it. But yeah. But yeah, the operation is given by the multiplication is given by the wedge. Is it?
yeah, so it's DA's can do this.
They don't commute, but
and
they don't commute, but by the surjectivity property, you can always write it as something in A, wedge B of something in A, B of something in A, and so on. If you want to use the universal property of the universal exterior algebra, there the action is clear because it's a sub omega 1 of u is inside A tensor. Here the operation is clear, and here this is a sublime module, so it has an induced map, and now we know that for every other algebra there is a surge action which I defined before, and that will give the right action as well, because this is a bimodule map. Okay, so this is our definition of Sn. Now, if we ask these mild conditions of omega 1 and 2 to be flat in mod A, which let me stress it again, is not a strong definition to us because omega-1 and omega-2 classically are vector bundles. So any reasonable notion of omega-1 and omega-2 should be at least flat. So if we have these two conditions, then we can interpret Sn into the tensor algebra, just like in the classical case. Not only that, but in particular, and this is the important one, we can interpret it as the intersection of the kernel of the wedge applied in each position. So this corresponds precisely to the classical situation. So why we chose the inductive definition then, if this one is more maybe intuitive? The reason is that the inductive one is the only one that gives us automatically, without any further assumption, the so-called Spencer complex. How does it work? So the elements of the components of the Spencer complex are theta complex, are omega k tensor sh, tensor composition of functors in this case, sh. And the way it works is the differentials are such that the quantum antisymmetric part increases and the quantum symmetric part decreases. How do we build this map? Again, we take sh, we forget the symmetry in the first component, and now we have omega k, omega 1. So now we apply the wedge with a suitable sign, which depends on the classical theory. We apply the wedge and we go into omega k plus 1 s h max. Now this complex with this sequence with these maps turns out to be a complex, because if we repeat this operation twice, what we are essentially doing is applying the wedge in the first two components of SH. This is what it corresponds to, and so necessarily it must vanish. So that's why this complex vanishes. We call it the Spencer delta complex, and its cohomology will be called the Spencer cohomology. And notice that the coefficients are swapped again for classical reason that they very understand. Fine. Okay, so let's go with the non-commutative generalization finally. So we start with the simple Moscow. Well, even before that, let me just tell you that the zero jet functor just needs to be the identity, because that's what we expect classically. So now let's go to the first degree, and let's consider a simple possible case. So we consider the universal exterior algebra, and as a module we take the algebra A itself. So classically this corresponds to taking the sections of the trivial bundle, trivial one-dimensional bundle. Okay. But since we define S1 to be omega 1 of u, and we know that omega 1 of u is the kernel of the multiplication, we have a natural short exact sequence. And now this is S1, this is just J0 of omega. So this looks very much like the jet short exact sequence. So what we do is we define the universal jet to be A tensor. Now, this is not the only way to define a short exact sequence. Turns out there can be more. There is only one way, only when the algebra is separable. But in the end, the one we chose has several advantages. First of all, it makes sense for row algebra. It's one of the few that makes sense for row algebra. And secondly, it's the one that gives classical jets. So it's a good idea. Okay, so yeah, we define the universal one jet as A tensor A, and the projection to be just a multiplication. And then we choose the prolongation to be right linear. This is because we ultimately would like to transform the jet functor into the jet one functor into a tensor functor. So in order to make sense to the prolongation also with the other bundles, it's necessary to assume that this is right linear. Okay. And this resembles a lot the theory that we saw last week. That's okay. So this is what we have now. We have the universal jet exact sequence, and what we would like is a jet exact sequence for a generic exterior algebra, in particular first order differential calculus. What do we have furthermore? We have an identity between the A's, and we have a bilinear map from the universal calculus to the calculus, the generic calculus. Okay. Now let's forget a bit about the left A module structure. So let's go in the category of right A modules. As a right A module, A is projective. It's free, so in particular projective, which means the sequence splits. And furthermore, it means that every given two maps from the extremes, they can be turned into a map from the extension. So we know that there exists, for now, only right A map between the two, which we call PHP. Okay, but now the category of right A module is an abelian category, so we can take the kernels and co-kernels. Turns out that well, the only spaces that are not trivial are kernel and co-kernel of the central map, which we know nothing about so far, and the kernel of this PD, which we call ND, and for us represents the first order differential relations of the calculus. Okay, so again, we're in an abelian category, so we can use homological algebra, and in particular the snake lemma. So we have a long exact sequence between the kernels and the co-kernels. And exactness now tells us that the co-kernel must be zero, because it's between zeros, and the kernel of this P hat map must be isomorphic to ND. So in particular, we can see that the one jet for a generic calculus must be a quotient of the universal one. Okay, good. But now this is not just a simple quotient, because if we look at the maps on the left, the inclusion of ND to omega 1 of u is an actual set theoretic inclusion, and the same for omega 1 of u into J1 of u. So we might as well identify the kernel of P hat D with ND. But now it turns out that this is a sub-bimodule of omega 1 of u, because its composition, the inclusions are bilinear, and this is submodule. So we can define J1 of D to be A tensor A over ND. Furthermore, we have the universal jet prolongation. We can compose it with a projection from the universal jet to the D jet, and we obtain the corresponding prolongation. So again, this is the explicit form of the D projection and the prolongation. In one case, it's the product of the equivalence class, and in the other case, it's the class of one tensor A. Okay. And now we can extend the notion of jet bundle over A to a notion of jet functor. And as I said before, we want to see it as a tensor functor. So the functor J1D will be the tensor on the left by J1D of A. Why does it still make sense? It makes sense because as right module, so this, if you apply the functor tensor over A by E on the right, all we care about is the right module structure. And as right modules, these sequences are split exact, which means any additive functor will preserve the exactness of these sequences. So we still get a reasonable notion of first order jet exact sequence. And so we have the jet, the one jet functor. Now that we have the one jet, we can generalize immediately another classical construction, which is that of non-harmonic jets, which are built in this way. So we apply the jet functor several times over a bundle, and we obtain this object, which we call the non-harmonic M-jet functor. Now this is a bit too big to be a reasonable notion of jet. Contains too much information, but it already allows us to formulate a notion of prolongation, which can be done by composing together the prolongations at each step of each time we apply a jet functor, we have a prolongation, so we compose them and we obtain a prolongation from the module to the non-harmonic jet bundle. Okay, how does this look like? So this will be a sequence of tensors. The way this works is by putting one, tensor 1, tensor 1, and so on until the last element, which is instead the initial element we started. Okay, so what else? We can take projections by applying the first grade projection in each component we want. And we already see a first problem of non-holonomic jet, which is the fact that there is no single projection. There are in general, n possible projections for the non-holonomic jets. So this is the first problem. It's too big. We need to at least restrict it to a situation where all these projections are the same. Okay. So let's see what's the actual 2-jet then. So this is what we want. We would like something. So now we know what S2 is. We know what J1 is. We lack an object in the middle. This is we want an object that satisfies this short exact sequence. Not only that, but another information we have is that we have this non-holonomic jet exact sequence, which is constructed by taking the one jet exact sequence over the one jet functor. So here you can see J1 of E, J1 of E, J1 of E. So we already know that this exists. And by classical theory, we would like these two to be related. So we would like a map between the holonomic 2-jet into the holonomic 2-jet. So notice that here we can take the identity, and here we already have this map, which first forgets the symmetry of S2 and sees S2 into omega-1 tensor omega-1. And then we have this map, which allows us to embed omega-1 into J1. So this already, what we already have. We need to find this object. Now, what's the problem now? We know that these iota maps are rejected, but we don't know if this is rejected because this functor might be wild. But if we assume it to be right flat, so flat in mod A, then it will be the monomorphism. And again, by the snake lemma, this will force this to be included. So, okay, so now the problem is to find a submodule of the non-holonomic 2-jet that fits in that short exact sequence. So there is one thing that makes sense. Furthermore, we also would like the prolongation to factor through the 2-jet. So we want the holonomic prolongation to coincide with the non-holonomic one. So what can we do? We can take everything that must for sure be in the 2-jet functor. For instance, we want S2 because we have an inclusion of S2 in the jet functor. So we take S2 inside of the non-holonomic S2, and then we take the module generated by the prolongation because we would like them to factor through the submodule. Okay, we take this submodule, and it turns out that it does satisfy the 2-jet short exact sequence. So this is the 2-jet. But okay, we are not completely satisfied with it. In fact, we would like to see it, and we can see it implicitly as the kernel of this bilinear map that goes from the non-holonomic 2-jet to this special module, which is a tensor. So it can be interpreted as a tensor functor as well. And it's such that as a righty module, it's a split, but as a lefty module, it has this strange action which mixes the value. So it has the standard action plus a central term which mixes the two grades. Okay, turns out that the 2-jet is the kernel of this map. This is the explicit form of this map. I will not go into details of it. I will just say that the vanishing of the first part tells us that the 2-jet projections coincide. So this solves the first problem. But it turns out that's not enough because the kernel of the submodule we obtain would just be too big, would just be the tensor algebra of degree 2. So we introduce this second option to restrict it to the symmetric algebra, symmetric space. Okay, so now we're in the position to do the same generalization that we did for symmetric forms. We did the same similar in style inductive definition of n-jet. And we interpret the n-jet inside the 1-jet of n-1 jets. Again, we can interpret this inclusion as a sort of forgetting the relation between the two components. How does it work? We again forget the information of the n-1 jet into J1 of Jn-2. We apply the 1-jet functor, and now that we have J1, J1, we can apply this map that we obtained. Okay, the kernel of that map will be for us the njet. Okay, not only that, but if we compose these inclusions by forgetting at each step the relation between the first component, we obtain the mapping from the holonomic njet to the non-holonomic jet, as in the classical case.
Can we define infinity jet into seconds?
We can. We just took the limit of the sequence, because now we have projections, we have the jets, so we take the limit. It can become problematic, but it's there. At least the definition is there. Okay. Okay, so now we can define the projections as basically the restriction of the projection of the first component after we apply this inclusion. So we see the njet inside J1, Jn, and then we project the first component. But as I said before, all the projections are fine, that they all coincide on the tjet, on the njet. Okay, and of course, if we compose this single step projection, we obtain a more general projection from Jn to Jn. Okay, we also, because of how they're defined, it turns out that the prolongation does actually factor through the holonomic jet. So we do have a prolongation from the identity functor to the njet functor. And not only that, but we have a way of interpreting Sn into Jn, and there is a unique mapping, iota, that's the missing data, such that it commutes in this diagram. What I will not go into details, but the only thing that I want to say about this is that what it means is that the operation of forgetting the relation of the first in the first position, they agree. Like this inclusion is such that forgetting the relation between the first position are the same. Okay. Okay, so finally the theorem that sort of justifies this definition. Under suitable assumptions, we have that the short-exit sequence does hold with the definitions we have given. Now, what are these assumptions? The first one we have I have several times said how they are to be expected in a sense, but the one that in a sense is kind of disturbing is asking that the Spencer cohomology vanishes. Now, this sounds like a strong assumption until we think of the geometric meaning of Spencer cohomology, which is associated to the solvability of the differential equation. And in particular, asking that the Spencer delta complex vanishes is the same as asking that on E, on the bundle E, the equation 0 equals 0 as a solution, which hopefully is true. And so I will rephrase this apparently strong condition into the following. Any reasonable notion of vector bundle, of generalized vector bundle, on which we want to build a theory of differential equation should have Spencer cohomology vanishing, if we want to hope to have some result. Okay, this is the main theorem. Other important theorems are this one, which essentially tells us that under reasonable conditions, the categories of finitely generated projective and flat modules are preserved. And in particular, why is this important? It's important because, as I said before, finitely generated projective modules correspond to the generalized notion of vector bundle. So what's this telling us is that the tensor functor, the jet functor maps a bundle into a bundle, which is the jet. So this is why this theorem is important. So it makes sense. Last but not least, we have this classical correspondence. So we know that when we take as an algebra A, C infinity of M, and as an exterior algebra, the drum complex, then the jets we obtain are exactly the classical jets.
Can you this is this algebraic geometry point of view jets?
Yeah, that's different though, because I think it involves the notion of total space.
Yes.
And it's dual as well. And we don't have a good notion of total space. I mean, yeah, we could proceed in like in the classical case, but it would be a very different theory. That's not approachable with this method. Okay, so let's see a purely non-commutative example now. in the universal exterior algebra. So yeah, I recall that the universal exterior algebra is just a tensor algebra over the kernel of the multiplication. So let's first describe the functor of symmetric forms, on the symmetric forms. By definition, the first two degrees must coincide with the exterior algebra. So the zero grade on E is E itself, and the one grade on E is the one universal form. So now we can compute the second grade, which is the kernel of the wedge, simply the wedge, because S1 of U is just omega 1 of U. For the wedge, we define the wedge to be the tensor product. So that's actually an identity map, and the kernel of the identity is 0. So already at degree 2, it vanishes. And for higher degrees, well, we know that Sn is inside of omega 1, Sn minus 1, and this is already 0. Also higher Sns are 0. So again, we see how the information given by the universal exterior algebra is very limited. But still, we can build this exterior algebra with these functors, and we can build the Spencer delta functors, and it turns out to be exact. And we can build our jets. And what jets turn out to be is, in degree 0, it's the identity functor. So the bundle is mapping itself by definition. And for higher grades, it's mapped into a tensor. Okay. Okay, the projections are just the well, unless it's the same. Oh, there is this. No, okay. So unless it's degree 1, 0, where it's the left action of A on E. In higher degrees, this is just the identity map, and the prolongation are, except the trivial case, they're of the form 1 tensors. Okay, and this is very reminiscent of the jets we saw last week, and I will point out at the relation between the notions in the last slide. Okay. Okay, perfect. And yeah, it turns out that without any assumption on Spencer homology, also because it vanishes, without any extra assumption, we get the universal n-jet short exact sequences. Good. Okay, so applications of jets. As we saw in the previous weeks, we know that differential operators can be defined using the definition of vanishing of nested Lie brackets. The problem is this makes sense only when we have a good notion of commutators, such as in classical geometry or in supergeometry. In general, the only commutator we have is the algebraic commutator and the one given by the associative algebra. And formulating a condition asking that a commutator must vanish in non-commutative geometry is a dangerous thing because it might ask too much. So we do the opposite. So we use the universal property of jets, of classical jets, to formulate a definition of differential operator, which we then generalize to our non-commutative generic set. So we can define differential operators as those maps of sections that are linear maps of sections such that they lift as bundle maps from the n-jet to the column. And if the grade is minimal, then we say if n is minimal, then we say that the differential operator has order n. Okay, now this lift turns out to be unique because every point in the bundle can be seen as the image by a prolongation. So it defines uniquely the lift, which means that we have that the functor of differential operators on n on E is representable in the category of bundles. Okay. So we take this definition of differential operator and we generalize it to the non-commutative case. So we say that a k-linear map that from E to F is a linear differential operator of order at most n when it admits a lift, an A-linear lift to the n-jet bundle via the jet relation. And when n is minimal, we say that that's the order of the operator. So in particular, we can see how differential operators order 0 are just a linear maps. That's because the 0th order prolongation is the identity, and so asking that it leads to an a-linear map means that it's an a-linear map itself. Another property that we can immediately give is what happens in the universal case. So it turns out that in the universal case, every k-linear map is a differential operator of order at most one, and it is a lift. So this once more shows how the universal exterior algebra doesn't really convey any further geometry. Like the only information is the one given by the algebra itself, which is what happens in degrees here. Okay. So what is a differential operator? Everything that we can expect to be a differential operator is a differential operator. So for instance, we have the exterior differential, we have notion of partial derivatives when we have parallelizable manifolds. And it turns out that with the notion of partial derivatives, we can formulate the Schwarz theorem also in non-commutative geometry. And it turns out that there is no generic commutativity between the partial derivatives, but we know that the two operations are quantum symmetric. So partial I tensor partial J minus the opposite turns out to be in S2, RS2. So this generalizes the Schwarz. Okay, what else? Yeah, the map that defines the jets, the two jets, is itself the lift of a differential operator. And now let's see the particular case of connections, just to give an idea. So connection can be generalized to the non-commutative setting by taking a map from E to one forms in E, such that it satisfies the Leibniz rule. So this is just basically repeating the definition in the classical case to the non-commutative setting. And it turns out connections are always differential operators. So this is the way we lift it. First of all, we lift it to the universal case, where we know how this map works. We have to apply the connection in the middle of the two. And then we notice that they vanish on the object ND. ND, which are the one relation, is the part that we have to push it out from the universal jet to the actual jet. So it turns out that they vanish there. So they factor through the quotient J1E. So it turns out that yes, connections are first order differential operators.
Is it applied in the reverse order that every differential operator of first order is?
No, not necessarily, because also zeroth order. Oh, you mean exactly first order? I don't think so, because you can always add the zeroth order differential operator to a connection. No, I don't think so. But yeah, so there is a something is strongly missing from this set of example, which is the derivations. Unfortunately, derivations in the natural sense are not differential operators, but nonetheless, we have a generalized notion of a way of interpreting each LNH vector field, let's say, as a differential operator. So we have a way of still conveying the notion of differentiating by a vector field, which is what derivations are in the classical case, to the non-commutative case.
What do you mean by vector fields?
We mean, so I can give you the definition and tell you what happens. So we define them as differential operators from A to A, X, such that they vanish on, I think, kernel of B. And it turns out, this looks weird, right? It looks like Y, but it makes sense classically. And it turns out that there is a correspondence between this object and with A, I don't remember here, maybe here, between omega 1 of the J, which means the U of the cotangent bundle. So the tangent bundle corresponds to this. But yeah, so this is what we have. So in a sense, the algebraic notion of derivation is not enough. So Leibniz is too much. Okay. Again, back to connections. Turns out that we can generalize without any assumption the classical result that connections correspond to splits of the one jet exact sequence. But this still holds in the generic non-commutative case. And okay, more properties on differential operators. So first of all, we can see differential operators as the image of the precomposition by the prolongation. Prolongation is k-linear, so this can be seen as a sub k module of k-linear maps from E to F. Not only that, but if we take a lift to the nth jet and we precompose it with the prolongation from n to m, then this is a lift also to higher jets, which means that there is a filtration of k modules with the degree of differential operators of a certain order with increasing with the order. You can consider the union of them, and that will be a differential operator of finite grade. This would be a submodule of k numbers. Okay, furthermore, notice that the zeroth order differential operator between A and A is just A op because we are considering the right multiplications, and so the order of the multiplication is reversed. Okay, now that we have a filtration of differential operators, it turns out we can also compose them. And without any extra assumption, we have that the composition of differential operators is a differential operator where the order is at most the sum of the orders of the other two. And the trick is the only missing ingredient is the top map, which turns out that we can not only forget the relation between the first two components, but we can really forget the information of relations at any other point. So n plus m jet is embedded into the m jet of the m jet. Okay, so this gives us a multiplication, and it turns out this multiplication preserves filtration, but not necessarily the grading. An example of that is the exterior covariant derivative associated to a connection, because this can always be produced in the same way as in the classical way. And we know it's not linear. It's not linear because connections are not linear. But we know that composing it twice, this gives us a functor of this form, which is classically is the wedging by the curvature. Notice that the curvature is on the right instead of on the left, as in the classical case, but this is how commutative geometry things work, because now it matters where we wedge. And this is a linear method. So this is a zeroth order differential operator. So composition of first order differential operators can be zeroth order. So only the filtration is preserved. Okay, so we can now define a category diff where the objects are alinear modules and the maps are differential operators. And we know that this category is enriched over filtrations of k modules. Okay, some final results. So a thing I have not discussed is, so I have showed how an exterior algebra gives us a notion of jets. I have shown how the notion of jets gives us a notion of differential operators. Now we have a way of producing from the differential operators the original calculus. So if we have a set of maps, k-linear maps, that we want to be first order differential operators, we can build a new calculus called the S-terminal calculus, such that it will produce jets that will give those, at least those differential operators. And when we have the set which is already a set of differential operators for a certain jet, that turns out to be exactly the differential. So this is a closure operator. So this, in a sense, completes the circle that jets are convey the same information as exterior algebra, and they convey the same information as differential operators. So we have this three objects. Yeah, basically it's three algebra. And this is the point, the important point that relates these jets with the ones we saw last week. Yeah, so which basically tells us that our jet can still be representative objects for differential operators, but that happens if and only if this map is surjective. So in a sense, if and only if the J n of D can be seen as a quotient of A tensor E, which is exactly the formulation of last week's test. Okay. What else? We'll have some more explicit criteria for k-linear maps to be differential operator. We can also define the notion of symbol of the differential operator. And finally, now that we have a notion of differential operator, we can also define a differential equation. We have several formulations. This is the more etymological one, let's say, where we say that we want to find objects, section sigma of E, such that sigma, once we apply delta, is equal to a section F of E. So this is just a normal differential equation, the classical style. But one could formulate things also in more aligned to the style of Noncommutative, and define this by seeing a differential equation as a sub-bundle. In general, it would be sub-object, but the best we can do so far is just considering sub-bundles of the mjet factor, and that's an issue.
Differential operators.
In the end, that could be equivalent, right? Because you can see the generic differential operator, which is not necessarily linear, as the map on which locally the phi t vanishes. Like locally, it's defined by differential operators. But yeah, anyway, the two notions are related also in the noncommutative case. In the end, it turns out to make sense. Okay, thank you.
Thank you very much. Nice. Sure. This is the right time for your questions.
When you say that the differential equations, which things that you put with your jets is the okay. It's hard to speak about the distributions.
Okay.
In non-commutative case, so it's Cartan distribution or the corresponding Cartan connection.
Yes.
So let's speak about connections.
Yeah.
Do we have
We don't have a notion of Cartan distribution yet, nor we haven't even thought about that yet. That's been, it's a question that it's a Damocles sword that's hanging. Yes.
Yeah, also maybe which related. Does it produce some extra exterior algebras? Because in a way, when you speak about
In principle,
distributions, because you need some exterior tangent spaces to your jets, because classical jets have on vector bundles, it's also manifolds, which is main features that you use.
Yeah. So if you have a manifold and you have a set of manifold which corresponds to an an algebra, and you have a set of k-linear maps between A modules that you want to be differential operators, then you can use the construction I was mentioning here, and that will produce a new calculus in general.
But I want to just for empty jets. Just for jet over my algebra.
Okay, without the calculus.
No, these are given calculus.
Okay.
Well, mostly maybe asking the same questions before. Well, how to produce an algebra from the jets?
Oh, algebra.
Because we need to be,
So the origin.
you want to be a manifold, so it should be an algebra.
I see. Yeah, no, I don't know. We always started from the data of the algebra is the only data we haven't ever left out. But so you have an object that behaves like jets, so it satisfies the sequence and everything. Yeah, I don't know. Hard to say also because for satisfying the properties that I've given, you also need to ask that there is a functor of symmetric Sn. And Sn already wants some notion of exterior algebra, and so maybe I don't know. Might be though, because like in the universal case, it's just A tensor A, so here's.
Well, I think the answer A is also a tricky object.
Yeah, true. Yeah, I've noticed.
And define maybe algebra structures.
The notion itself of separability surprised me a lot, like the fact that there is an element in the algebra that should be everything but commutative data. So there can be an object that commutes with everything, nonetheless, inseparable. Yeah, it can be a tricky object. Yeah, I don't know.
So, any other question? Maybe I would have one. Do you have any geometric interpretation of your non-holonomic jet bundle? How they relate to those holonomic?
Yeah, so the non-holonomic jet bundle. Okay, let's say the n-jet bundle represents the nth order approximation of a section. But then it means that you're, in a sense, working only with the fiber data. So the difference is that when you take the non-holonomic 2-jet, for instance, you're taking the jet over the jet. So it means you're not really looking at second order approximation, but you're looking at first order approximation of first order approximation. And there is a certain relation between the approximation of the fiber and the approximation of the base.
In coordinates, for instance, if I
I'm not good with jet coordinates, but I think it all boils down to the fact that from the non-holonomic case to the holonomic case, there is a derivation of the base approximation and the approximation of the fiber. And these two must be related. I think in the two.
It resembles something. It resembles to me something what's called higher differential forms like gorms or worms defined by Paolo Schivera. When you take functions on shifted tangent bundles, it's canonically identified with something like forms, which poses more information. So I think it might be somehow related to my question, but don't know exactly how. Any other question?
Just related to so the crucial difference between localities and yours is that your jet calculus depends on the choice of exterior algebra.
Yes, but actually, so if you take the exterior algebra, I haven't proved anything about this, but I think that if we take a reasonable notion of exterior algebra coming from supergeometry and we change the signs in a reasonable way, we can find an equivalent formulation of supergeometry so that if this map, so that this map will be surjective and this will coincide with the jets we have seen from here.
Otherwise, it's just defined as functors in case of modules. Some parts are reaching my equivalent. For example, if I check algebra A and algebra matches over A.
Okay.
So the categories of modules are not to be equivalent.
Okay.
So in this case, I guess. Yeah, but again, is the choice of
okay. But yeah, the exterior algebra is given in the context of supersymmetry. Well, okay, it's an initial data, but it's also a different data because the grading, the multiplication works in a different way. But if you change the sign of the grades in a certain way, I think you can formulate it in this context as well.
Okay.
Also, another difference with the Jan's approach is that we have only dealt with the global setting. So we, in a sense, we have assumed the self-swapping. But my feeling is that if you do the so if you have in general, you don't have a good notion of locality in a non-commutative space. But when you do have it, like in the super case, then you can do this construction on each open, and then you can sheetify and obtain the corresponding motion of the jets that, yeah. I think this is the operation you have to do. So in general, you don't have a good notion of locality, so it's not it's not feasible. But when you do have it, then yes, you can take sheaves. We can take this construction locally and then sheepify the object. This is my impression. Again, nothing is proven about it, it's just intuition.
Is it interesting to think about some concrete examples of algebras?
Yeah, we are actually working on that. We have so far we have managed to prove that the quantum CPN works. But there are good signs that show that it's reasonable to assume that everything works, because what we did essentially depends on representation theory. So in the context of quantum groups, quantum manifolds, everything depends on representation. So it makes sense that it would be weird if it didn't work anymore just for this quantum thinking. Yeah, still to be proven in mostly.
It still proves that the functors are equivalent.
Equivalent. Yeah, they are equivalent. Yes. They are equivariant, and everything lifts. So we can go through Takeuchi's equivalence. One problem we have encountered is that so the one jet bundle is not in mod 0, which is the category, the part of the category which is monoidally equivalent. So that the monoidal structure, so the tensor product is not preserved. But yeah, we're working. We have good ways around. So soon.
And if A is, for example, deformation quantization, say in the sense can be formal, would it make sense? Like
I don't know.
so you don't know.
I don't know.
Converge, but like nice. Formal power series.
Okay, I don't know. Should be look into it. I don't know. Very little.
It should work, but everything works.
Yeah, obviously.
Okay, so if there's no other question, we thank our speaker for a nice talk and answers. Thanks.